Hello, everyone. Welcome to another BAF event. Today, I'm very happy to have with me Lincoln Moore from Vanderbilt University. And presenting today is going to be Fluence. A lot of good stuff, a lot of interesting. Was talking to Bernhard before. It's a very interesting project. We're looking forward to hearing more about it. Just a little intro about BAF. We're a 501c3 nonprofit that works with universities' blockchain clubs in accelerating blockchain education, working on projects, starting accredited courses, and also placing students at jobs in the industry. So if you're interested in getting involved, we have a membership application that I highly recommend you take. That's how you get access to the network. It's completely free. It's our proof of work. To show that you're actually interested in this industry and in the tech, and not just because Dogecoin went to 42 cents the other day. But besides that, I let Lincoln take over, introduce our guest. If you have any question, please drop them in the chat, or there's also a Q&A section. You can also upvote other people's question. Yeah, other than that, Lincoln, you can take it away.
Yeah, thank you. Thank you so much for being here today with us. I'm here with Bernhard Borges, scientist and engineer at Fluence Labs, and he's going to start out with a little presentation he's prepared included. And like has already been said, if you have any questions, please leave them in the chat, and we'll either get to them during the presentation or at the end. So Bernhard, take it away.
All right, got it. Share. All right. Thanks for having me, and let's get going. So I prepared a little presentation here, and I gotta see I would like to keep seeing the chat window. Let me know if it's too small, then I can blow it up. So the title of the presentation, or the topic we really want to get to, is program distributed systems with Aquamarine, and we'll get to that, what that is, in a minute. So what is Fluence? Fluence builds open source peer-to-peer networks and associated components, support system, and tooling, and a lot of it is actually based on Rust. And our goal is to really empower developers to successfully build distributed and particularly peer-to-peer applications. And there's a little bit more to building peer-to-peer applications than just slapping libp2p together, even though that can be challenging for anyone who ever tried. And to that end, we have an open source offering. It's total open source. I think it's Apache 2.0. And it's a runtime and a program environment to enable peer-to-peer choreography and composition for peer-to-peer applications and backends. That's something to unpack over the next few slides. So why do you need distributed programming tools? One of the interesting aspects of peer-to-peer is how you can change the request response paradigm. That's very, very different from a client-server perspective. So in a client-server perspective, you generally have a request response pattern that's sort of end-to-end, right? You have a request to some API, you get the response, you get it back to your client, you send it out back to the response. So if you're trying to authorize a credit card, for example, and then want to send a SMS to your customer, you hit the swipe API, you get the response back, and then you go to Twilio and you send the SMS. In a peer-to-peer environment, the possibility literally would be you hit up swipe, and then from there you go straight to SMS. And that's a very, very different paradigm. However, that just doesn't fall out from using peer-to-peer. You actually have to work for it. And this is where Fluence, and in particular Aquamarine, comes in. It makes this work for you very, very easy. So what's Aquamarine? Aquamarine is a set of technologies to program distributed systems. It's comprised of two languages. One is a high-level scripting language called Aqua, and the other one is a low-level language called Air. And it has two VMs. The Aqua virtual machine runs Air on each peer. This is key, because this is where, quote unquote, your routing comes in. And there's Marine, which is the virtual machine that runs the various WebAssembly modules with AVM compatible interfaces on each peer. So that enables you to do actually a lot of things, including separate your orchestration, your workflow, from pure service business logic. That's actually extremely powerful. And that's really what makes peer-to-peer applications. The other major attribute of Aquamarine is, from a design perspective, it has zero trust applications as a first citizen. And by zero trust is basically you have to authenticate and authorize at every step. There is no exceptions. There is no carryover. There is nothing for free. And that really gives you application collaboration or composition over peer-to-peer networks. So in order to get this done, you got to have a foundation, because one of the interesting parts of peer-to-peer networks is that dropping a peer is an expectation, not an exception. So in order to model and even formally verify your systems and your topologies, you need to have a calculus that actually allows you to do it. And PyCalculus is exactly formulated for that purpose, basically mobile topologies, where mobile means changing. And it's got some interesting and small set of operators, just like lambda calculus and most of the calculi, which end up actually giving you a huge repertoire of capabilities. So what does it all look like in real life? On the left, you see sort of what the language foundations are in terms of instructions. It's not entirely complete, but it gets us through what we need to do. And I think they all look very familiar, right? You got an execution, you can process sequentially or in parallel. You have iteration, you have branching, and then you got an identity. So in that lower level language expression, which is in the upper pink bar, what that says, basically, it says we want to call function put from service DHT on peer 12D3 node with the argument as key value, and we expect a named output called result. That's it. But as you can imagine, once you string a bunch of those instruction sets together, you actually can program your peer-to-peer application extremely effectively and quite powerful. So we talked about services. Well, I talked about services and workflows. So where is this whole, what happens to the data? Is it just, I mean, it's not just out there on the network, right? I mean, we say it's out there on the network, but it's not just there. It's very deterministic. And to that extent, we built we developed a concept called a particle. And particles are conflict-free data replication data structures that combine data and execution sequences, such as the lower level language example given on the right. So basically what happens is, as you work through the workflow, these particles just basically hop from peer to peer and interact with the services they're supposed to, make their calls, and just keep moving along. And to make this a little bit more graphically appealing, on the left, so let me show this sort of in a bit of a context. On the left, we have a Kademlia network, which is the big circle. The network is comprised of a bunch of peers, which are the whitish rectangles. And in those nodes you have, or peers, you have services, which are the little round dots, 1, 2, 3. You could have 1,000 depending on the capability of the node and the capacity of the service. And what's happening here is, you can think of it as a chat application. Firefox is a client, is a peer client, and Chrome is a peer client. And Firefox now wants to send a message to the Chrome client. And we want this message to be not just text, but we want to have, I don't know, an emoji with it. And we want to have some additional text formatting done. In the traditional client server environment, all of this would be happening at the right there at the browser Firefox client. In the peer-to-peer, assuming we have the services deployed on different nodes, what happens is you write the text, you have the specs for adding emojis, you add something else to it, like, I don't know, maybe upload a file, whatever, and then it goes to the Chrome. So a very stylized example, but you see what's happening, right? You have super thin clients, and those clients can be deployed just about anywhere. The VMs we have are themselves WebAssembly modules, so they deploy in very thin clients, including browsers, IoT devices, and what you get is extremely powerful network capabilities controlled by extremely thin clients on very, very cheap hardware, if that's a design requirement. So I told you that one of our goals is to make it easier for developers to program those kind of applications. And then I gave you the example of the lower level language, which is on the right here. And obviously that doesn't necessarily make it easier unless you have very dedicated Lisp or schemer, right? So we have this higher level language I told you about, and that's on the right. So this generates the lower level language. And basically what it does is, so we specify a greeting service interface and the function greeting, which takes a string and a bool, and we'll get to this why. This is a very fancy hello world, taking two variables. And this is the interface. This is not the service. So you can think about it, if you're coming from a blockchain perspective, you can think about it sort of as the ABI of the service. This is not the ABI is not the contract, and this is obviously not the service. And then we associate the service with basically an execution statement. And what we're saying here is on the input variable, so we got the name, Joe, we got the greeter, which is our Boolean, and then we get the node identity, and we get the greeting service ID. And then we execute, when it comes to it, that function, which basically says on the node specified, just like before, call node 12d3 node, I think it was, for the greeting service, where that's the service ID, and then call the actual function greeting, for which we have our shim up here, and then we return a result. And that gets translated into this lower level language, which then runs at the interpreter at the peer level. We even went a step further. The same thing, what I just showed you, you have the option to get it nicely wrapped into an async function for your TypeScript. And you're basically like 90% where you need to be. So that's super, super convenient. So now, what are these services? How does this actually all work? On the left, I'm giving you the Rust code for an echo service, and this is just a proxy. It could be a SQL call, it could be a database, could be Redis, could be anything. It's basically, it's a service or it's a module that takes an array of strings and returns an array of structs. And it's written in Rust, and we have an SDK, which then where the compile target is WASI 32. And on the right, we have a greeting service, our fancy hello world, which takes basically the string, the name, and the bool we talked about before. And basically, if it's true, it's a hi, and if it's false, it's a bye. So that gives you the core of services you can deploy on peer networks. And the echo service and the greeting service, they don't have to be on the same peer, right? They can be on very different peers and on multiple peers, which really, really showcases the what you can do by separating the workflow of choreographing those services into an application. And I got a couple examples we can just get through so we can have a little chat, a Q&A. The first one, basically, so those are the same two services. And what we have here is we have the echo service on node 1. And the echo service, we basically give our names, the array of strings, and it'll be blockchain, association, foundation. Those are our 3 names that are going in there. And we have our greeting service, and we actually have 2, one on node 2 and one on node 3. The services are the same, the inputs are different, right? And since we know we have 3 inputs, blockchain, association, foundation, we just decide we only want the first and the last one, so index 0 and index 2. And then we want to get back our result. And as this executes, what you get back are those lower 2 lines, basically high blockchain, high foundation. So that's kind of lame, right? Because, I mean, how many times do you actually know what the input size is of your array? So what we can do is we can use the fold or the iterator command operation I showed you before. And in this example, now we again have the echo service on node 1. But in this case, we just call one service on node 2 and iterate through it. So again, with those 3 inputs, we get our high, high, high outputs, just as expected. Finally, a slightly different take. We still get the echo service on 1, and we get our greeting service as in the previous example on node 2 and 3. However, this time we process the outputs from the echo service as they come in, but we use different greeter booleans. So now we end up basically with the parallel processing, because we're executing on different nodes, services on different peers that allows us to parallelize the call. And we go from high blockchain, high association, high foundation to bye, bye, bye. So that shows you how a couple things. First of all, you can do a lot with just a few operators. It's actually extremely powerful. Second of all, it shows you how you can reuse basically services that are decoupled from your workflow entirely, and that actually makes for great efficiencies in writing your programs. So now you say, well, what about security? So this is all nice. You got a peer-to-peer network. What are you doing about security? So in security, we have what's called a security tetraplet, and basically it combines. It's a data structure that combines peer ID, service ID, function name, data getter, and a few other things that are included in tetraplets, such as the public key and the signature of the application initiator. So what it basically allows you to do is it allows you to securely compose functions within the execution script. And so if you're still with me, hang on, let me. Do you see that? No, you don't, right? Sure. Okay, so this is of course super small. So the way it works is basically, so this is a slightly different greeting. It's a simple greeting just with a basic string. It doesn't have the Boolean, but it doesn't really matter. So basically, how you can write your service is you can authenticate whether or not the caller is the owner, which is very similar to what you do in smart contracts and most blockchain applications. And the way this is done, so basically, if you resolve to the owner, you get to do your greeting. If not, you get kicked out. And the way this is done, and this is where the tetraplet part comes in, is basically here. Let me make this really big. So we added a function here, basically is owner. And from the Fluence SDK, we can get our call parameters, which includes all the peer ID, the public key, all the signatures, all that good stuff. And then we can determine the identity of a caller and the identity of the owner. And if those two match up, then we know the owner is the caller, and we can grant authentication. And that's exposed to a very simple function, and my owner. Just going back to this, and it's right here. And this is extremely powerful because it lets you build very, very fine-grained IAM-like capabilities at the API function level, so function as a service type level. And this is easily extendable and fully enforceable. So instead of just thinking about it as an owner caller, you can now start building user lists just like you would, I don't know, like in Amazon with IAM, and start associating fine-grained capabilities and authorizations to that user list. So before we get to Q&A, services are business logic Unix composed from shared nothing WebAssembly modules. And you've seen this, those modules don't share anything. They just expose APIs. And particles called services, and then it just hop along, which is, to me, it's a very nice visual, programmatically specified along the nodes and interact with those services. And Aquamarine really allows you to do that. That was really, if you only take one thing away, basically it's Aquamarine allows you to program peer-to-peer applications very, very efficiently. And this was sort of the end of powering through the presentation. So obviously, one of the reasons I went through fast is to set the table for the discussion. And I think Lincoln's gonna start leading that.
Yes, perfect. Thank you so much for the presentation. So one of the first questions we had was about, could you expand on this concept of a service comes to a node, and what can the peers do with this?
Okay, so a service is fundamentally three things. A service is one or more WebAssembly modules and a configuration that associates those modules into an API. We call that a blueprint, and with that you then get a service ID. So when you deploy a service, what you're actually deploying is you're sending those WebAssembly modules plus the blueprint plus the blueprint to a node or more than one node, and then you get back your service ID and some additional information about the node. And that now basically enables a node to host the service by basically exposing the API, the public or private API, if the right credentials come in, to whatever workflow, whatever particle comes along. And so the node itself really doesn't do anything or get anything from it, at least computationally, from the service. It's just basically it hosts those services and has pre-built the virtual machines or the interpreters necessary to have the particle interact and keep routing in the right hops along the way. That answered the question?
Yes, that makes a lot of sense.
Good. All right.
So when you're coding these particles to hop along, do they go for a service or do they go for a node? Like, what would happen in the case that a node is down when it's expected to be up? Is there some sort of fail-safe in that situation?
You can have it. It's not out of the box. So basically what would happen is, let's just say you have one service on one node. So the first, so in your Aquamarine workflow program, essentially in your choreography program, you specify first go to service A, add an emoji, for example. And this is on node 1, 2, 3D, whatever I showed before. And this is that service, and we call this function. So it starts basically, it's sort of like the client, let's call it Firefox. The client's job literally is just to like fling that particle, which has the workflow instruction, programmatic instructions as its part, to the first or to any node at the network, the first relay, which is the first public peer, which may not necessarily host the service. And then through lib peer-to-peer and through the virtual machine, it gets resolved where the particle has to go to then add the emoji to its data, I don't know, data pack, if you will. And then the virtual machine looks what the next instructions are. If there's nothing next, I mean, if there's nothing else from a service perspective, the next hop would be Chrome, right? So now we got Chrome, we got basically deliver result, and we have the node. So now it resolves, and hopefully it's a straight shot to Chrome. And all of a sudden, you have my hello with smiley face on your chat window.
Fascinating. It seems like a great way to keep that decentralization while also making sure that there is like a guaranteed way for it to go through without there being any errors, which is obviously very important when it comes to data.
Exactly. And this is why Fluence itself doesn't have a consensus protocol per se, because the nodes don't recalculate what you've done, but you can verify that your data particle has transferred correctly. So instead of rerunning everything, it's really fundamentally, I should have said this before. One of the really cool things that happens is when you do what we would like you to do is every application through its workflow, through its choreography, creates a temporal virtual private network on a permissionless peer-to-peer. And that's actually, I should have led with that actually, because this is actually really, really powerful. I don't know why I forgot that, but I just want to make time, I guess. But that's really, really powerful. And that's where that's your reference of validation, and it's all about the data and the execution structure. So I told you before, I'm not big, I don't think necessarily analogy is always helpful, but if you look at it sort of on the blockchain, every node reruns the complete last block. And to me, that's sort of a vertical approach to verification, whereas in our system, which really has nothing to do with blockchain but augments blockchain, it's a horizontal verification, right? It's very local to your application.
Fascinating. So, can anyone run a Fluence node today? Is that available? That was one of the questions from our chat.
Yes. So yes, you can run it, and now it gets interesting. We have a few minutes, right?
Yeah.
Okay, so let me back up a little bit. One of the reasons we're doing what we're doing is, aside from making it easy for developers to develop really, really cool, efficient, and decentralized applications, is to really deal with the issue of decentralization in general compute platforms. And one of the issues we've been seeing is that the big cloud service providers really have been doing a lot of value capture, extreme value capture on open source projects, where open source projects basically see their work being monetized in interesting ways, and there's nothing really coming back that way. So one of the things we're developing in parallel is a blockchain, well, not really a blockchain, but a blockchain context that will allow developers to create licenses for their deployed services on the blockchain and monetize that if they want to. I mean, you can do it for free, but the software license is really, it's a hosting license. It's not a service, not a software license per se. So it's not really like, oh, this is MIT license or Apache license, we put it on. It's really a license, a use license for the service. And you can make it for free if you want to, or you can charge for it. That's
sort of like a royalty.
Yes, but it's up to the developer. It's the developer getting the royalty, not us or anybody else. It's the developer. So one of the really cool things that happens is that if you look at dependency graphs of a lot of projects, is that a few very small, relatively small, but super critical libraries are just everywhere. And usually those really important but small open source projects are totally a labor of love, because they never get anything because they're so far down at the stack, yet everybody depends on them. And if you start thinking about this from a service license or use license perspective, they actually would make out, quote unquote, like bandits, because they really would get the pyramid benefit of everybody reusing their work, which is actually what they should be getting, right? I mean, that, at least in my opinion, if you're at the base layer of a whole bunch of technology stacks, you seem kind of important, and that should be somewhat be reflected, and not just anyway. If you want it reflected, if you don't, then you don't. That's fine. So, but the blockchain itself has nothing to do necessarily with the Fluence peer-to-peer protocol. It just enables participants of the protocol to stake out their claims much better than they can today in any other system. And that brings then some other interesting aspects to it. in terms of how you do how you bridge trust gaps, because in the real world it's not as black and white as we often would like to see in terms of trustlessness. And one of the things is, if you run services on a node that's not yours, it's just like if you run something on a big cloud provider, you don't know. You cannot assume it's not malicious. Where malicious doesn't have to be criminal. It just could be negligent. It could be unavailable. So there are certain guarantees you can enforce through smart contracts, which actually would make it much more palatable, in my opinion, for developers to use other nodes than having to run their own node.
Okay, yeah, that makes a lot of sense. It gives these open source developers who have contributed so much an opportunity, but not necessarily an obligation, to make a little bit of incentive off their work, while also incentivizing them to encourage use of Fluence in order to make that the royalty off their work.
Yes.
All right, great. So segueing a little bit into one of our other questions from the Q&A. So what types of DHTs are supported, and could we do ad hoc unstructured ones?
Okay, so what we're doing, you basically, you could build your own network whichever way you want, because the VMs, you just, I mean, as I said, they're open source. You just pull them in, and that's fine. We're right now at Academia. That's really where we're looking at the most, and DHT. And what we want to do is, and that's what we're working on right now, is we want to be able to program DHT as part of the Aquamarine system. So push it up. So you're not just using Aquamarine to program the workflows for your services, but you actually program your configuration of the network, or of your node, and partially of the network. And one of the aspects, and one of the capabilities to do that, is that we've sort of built services into the node that allows you to use that high-level language, or the low-level language, if you're a real glutton for punishment, to program the node and thereby the network using that. So in many respects, yeah, you can fiddle with it, but our approach right now is just XOR DHT and Academia. That's really where the out-of-the-box experience comes from, if that's how you want to call it.
Yeah, okay, that makes sense. So another question we had from the chat is, what happens if we have routing that requires logic that can't be described in Aqua, such as a route table constraining to prevent poisoning, or locally aware partition resolution algorithms, etc.?
Well, let's put it this way. If you can't express it in Aqua, then now I really got to work on my French here. Then you had a shit luck. Sorry, because it's just not there. However, we are pretty confident that you can express just about anything that can be formulated in mobile concurrent topologies can be done. However, it may take a little bit of rethinking of how you're doing it, in part because you're really decoupling things. Now, what was the last part of the question? What was the example given?
A route table constraining to prevent poisoning, or locality aware partition resolution algorithms.
So a lot of this. So okay. So one of the things we have. So now we're going down the stack, which is cool. One of the things we have the notion of a Truss Graph. It's not part of Aquamarine, but it's part of the Fluence stack. And the differentiations probably start getting a little blurry, and that's fine. And the Truss Graph basically allows you to assign, subjectively, weights to other nodes. So it doesn't just use the weights of efficiently finding nodes, which you get through Academia, but actually it allows you to literally allocate weights to nodes. And through this specification, and it's subjective, right? I mean, everybody's Truss Graph would be different. This is where I sort of started poking a little bit before. Trust is I mean, it's in in the real world and in the unconstrained world, trust is something a lot of people invested a lot of time in and money in, and to just utterly ignore it may not be necessarily the most prudent way for a large open system. That's why it's very different from a blockchain system, right? And so if poisoning is an issue, that's really at that lower level. And aside from the Kademlia guarantees, we give you another tool to deal with weighting other nodes, and that should massively eliminate, if not entirely eliminate, any kinds of poisoning problems at all. So there is just sort of thinking out loud. One of the things I've sort of been fiddling with is basically using token curated registries to basically derive automatically a subjective weights for these truss graphs. It's very early on, but if anybody's interested, hit us up. We might be able to do something with you on that. It's because that's where, again, this blending of trust and trustlessness could come in. If you know the nodes and you know subnetworks, then you don't need TCRs. But if you don't, TCRs could be an extremely helpful tool in bridging some of those gaps. I hope that answers the question. If not, hit me up again.
I'll keep an eye out for that, but it seems good. So another question I had was, is there any way, and I think you've hinted at the answer to this, but is there any way for the ecosystem and the network to be able to interact with nodes that are outside of the peer-to-peer network you have?
Yes. Okay, so this is, I shouldn't have put such a strong yes to it, because obviously that's not really the world we envision, right? But it's obviously going to be a journey, and so absolutely. So one of the things you can do is you build a call it an adapter service that then is your relay or your proxy into other nodes. And this is, for example, we've done some examples around, especially around Denver, basically using a decentralized Oracle feed. And that's basically what we've done, where we basically wrote some adapters, pulling from the event logs, and and then just routing it through the various application stops. Now, one thing that's really important to know is the following. Services can't call other services with those kind of scripts, because that would just cause havoc on everything. And so when you design your application, particularly if you're writing the service itself. So in an ideal world, you sort of have hosters, right? I mean, people or entities operating nodes. You have developers that develop services, and then you have consumers of those services that just basically compose applications. So I mean, this is sort of, but this is sort of the ideal separation of labor, division of labor, but obviously that's not how it's going to be. And you write your own services, and then you write your own application, or at least part of it, and you fiddle with it, and reuse, you build on top, fine. And that's exactly how it's going to be. But that's where you have to redesign a little bit, and you mentioned what you're dealing with, because you really got to look at it from a topology perspective more than sort of a cascading data flow or data logic perspective.
Okay, that makes sense. It's good that that option is there, though, even if it is slightly more difficult than the regular implementation.
But the adapters are just fine. I mean, in many respects, it's just another service, right? It's just another service. It's and if you are happy, so somewhere I have it. It's somewhere in the examples on in our GitHub repo. If you want to use swipe, you can. I mean, it just you basically re-implement part of the API. Basically what you need to do, it's exactly what you do if you write a Rust SDK or a Python SDK instead of just a REST API call, right? You basically re-implement those exposed functions, and it's the same thing if you write the adapter, but it's probably more narrow because you have a particular use case in place. But yes, so it's not an island. It's part of the big picture.
Interesting. All right. So another question we have from the chat is, how much can we specify how these hops happen? For example, could we say to handle these hops iteratively to come back to the sender after every hop versus recursively only returning the response to the sender?
Yes, you can. You can, but ideally, ideally, you don't want to go back to the sender, right? You just want to keep going forward until you reach your objective. But yes, you can. You can also specify exactly which node you want to use. So if you, if a service is deployed on 10 different nodes and you have your subjective, you put the effort in, you have your subjective trust weight for nodes, you can specify which nodes to use just based on the weights alone.
Okay.
So you have huge control. But of course, with a lot of control comes a lot of responsibility, right?
Absolutely, yeah. So could you elaborate a little bit more about the service discovery and how node discovery happens for the DHTs? And if through Fluence, how node discovery happens while you're plugging into Fluence, if that makes sense?
You start out, one of the things we are working on right now on different models, but my favorite is still you have the bootstrap model of initial discovery, and then you use the XOR distance difference between closest nodes. So that's one. So that's your basic, as far as I'm concerned, peer-to-peer DHT Kademlia approach, or Kademlia approach to it. Depending on where the services are, it gets a little more tricky. And this is why you actually specify the nodes with the service in your workflow. So now it's not sort of a blind discovery, if you will. It's very deterministic of where you want to go. So what constitutes then just a node behind the relay and actual relay really comes back to the discovery at the low-level protocols. And as I said, so its nearest neighbor is pretty much the driving one, and then your selection criteria in terms of your trust weights is basically the final deciding effort. But in terms of so it's not any different than how you do it in IPFS or Ethereum or Substrate for Polkadot for that matter.
Yeah. Okay, makes sense. Seems like the industry standard in that case.
Yes. Rust lib P2P, and then slap on some homemade goodness, and you're good to go.
Exactly. So you mentioned that the people who make the money off of the hosting the node are the developers who made that code. Is there any monetary incentive to run that Fluence node?
Yes. So I would. It's we don't give you the economic regulations on how you need to do things, but I would suspect that a node operator who runs services would like to get paid as well, particularly if those services are being charged for. And this is what you can specify then is part of those service contracts between the node and the developers and the user of those services. And that's under active development. Hopefully, like, I don't know, July, August, we should have something pretty decent out there, and beta or test network. And yes, so node operators certainly can follow the general cloud service operating model, and I don't know. It's like a lot of commercial separation between for charge and no charge. I would absolutely expect node operators to not do it for the goodness of their heart.
Yeah, that would only make sense. So why, another question from the chat is, why are the verifying orchestrations are needed, assuming we have verified and or model checked the specs?
I think so the model verification itself is I think you want a framework that allows you to reason about your topology and how you traverse the topology. And I think it's important because the topology itself is dynamic. So things come and go. And if you end up with a failure, I think it's really important to know whether that failure is because that service just wasn't there anymore. If it's not there anymore, it's just not there. There's nothing you can do about it, right? It's just the I don't care how many DNS lookups you have. If the service isn't there, it's just not there. And but you want to be able to tell the difference between what's simply not available versus what was a failure in the routing. Those are two very, very different things, and I think it's really, really important for application developers to be able to discern where a problem comes in. And this is why, in many respects, going back to this whole p-calculus thing, this is where this comes in, this whole modeling and reasoning about topologies, so that you have a good experience. And even though you're operating in a dynamic environment, you still got a determinism there that allows you to follow through and make sure that things happen the way they're supposed to happen.
Okay, that makes sense. So another question I had for you is, what do you think the biggest technical hurdle for the average developer who wants to start using Fluence to get started?
So you can use it today, and we got multiple projects using it, and or in the process of using it. It takes a little bit of elbow grease, but the reliability of the system is there. It's the features. It's not fully feature complete, but it's quite feature complete. The documentation, I'm looking at myself here, is probably not as good as it could be, because the trade-offs, we're a small team, so there are trade-offs to be made. However, I do believe we are very, very welcoming to people asking for support on any of the channels. And through GitHub, and so, but you need a little bit of drive. I mean, it's not different than if you've never done blockchain and you start like hacking, writing a Solidity contract, whatever, right? I mean, it's not, even in 2021, it's not the smoothest of experiences compared to, say, writing a Delphi integration of two SAP systems, right? So, but I think it's certainly doable, and I do believe that the majority of the people who go on that adventure have very interesting ideas of what to do. And I can't say too much, but one of it is, I mean, messaging is a huge deal, right? This is, I mean, not just in terms of chat, but in terms of machine-to-machine messaging, Oracle production, if you come from, or relaying, if you come from a blockchain perspective, but also using thin clients to do very, very difficult things. So, for example, if you're in the business of, if your application requires you to generate zero knowledge proofs, for example, where do you do it? I mean, you don't necessarily want to do it on the client, and this is where those distributed services come in actually extremely handy, and where the node carries a lot of the computational capabilities. And the other thing is that once you sort of fling that particle into this, topology with its execution stream, sure, it may take a certain period of time to calculate that proof, but then it just goes forward to your financial institution, whatever, or whoever the verifier is going to be, without your client having to hang around and pull and pull and pull and pull. And that's actually a very, very, there's a couple people working in this area, and this is a great, great way of getting the motivation to overcome the early adopter obstacles if you're in that space. So there, there are a few other NPC areas that are highly applicable to pushing some of the dealer requirements in some of the cryptographic protocols away from the client.
Interesting. Okay. All right. So we have time for a couple more questions. So if anyone in the chat wants to ask something, now would be the time. One of the questions is, how can you verify that a node does the correct computation?
Okay, that's fundamentally, the node doesn't do the computation. The node provides the environment for the computation to take place. So there are a few things we have in place, which I didn't go into in detail. One is at every step, your data, your particle basically gets signed, and the inputs get signed. So you can verify that your data inputs are the ones you wanted, that were supposed to be, and that the output is what your next input is, that it's correct. So that you can verify along the way. The other part is we got a very strict, and part of it is actually it comes doesn't come free, but it comes with WASI 32, because we're using it with the interface types. Is that we got very strict type checking at the service level, at the module level, at the WebAssembly level, and that also helps you put guards in place against corruption. Now, if you're looking at how can I guarantee that a node operator does not mess with ephemeral data and give me wrong results, that's where you don't have absolute proof as part of the transaction. So if that's an issue, just like, I mean, this is basically saying, how can I trust Amazon that they don't change my results from my call, right? I mean, you trust Amazon not to do for you. I mean, this is not any different, and this is a problem. It always has been a problem. It always will be a problem unless you run your own infrastructure, right? But even then, if you run your node, say on Amazon, how do you know that Amazon isn't, or I shouldn't say Amazon, but the underlying infrastructure provider isn't messing with your system? So we have signed signatures along the way that allow you to verify a large deal. But if you have a very dedicated malicious operator, then you're just about, then you might be exposed.
Yeah, well, that seems to be one of the beauties of the decentralized network, is that if you do find that there is a bad actor, they can easily be replaced, and they have an economic incentive to be replaced.
Right, and that's where now all of a sudden, when we start putting service licenses with blockchain, with incentives around on the blockchain, which, even though the operation is separate from the Fluence network or the peer-to-peer network, the incentivization certainly transcends that separation. And then all of a sudden, you can put these guarantees in place. So if I have a service that I need the utmost reliability from a node operator, I certainly can make sure that I get the financial commitment from that node operator through the blockchain system to, be penalized if things don't go the way they're supposed to go. Obviously, I presume that that node operator would also charge you more, because if they're on the hook for that, right? But yeah, so run your own node. I mean, if it's mission critical and you don't have the trust in the network then you literally have to run your service on your own node.
Yeah, that makes sense. But there's also that second layer of the developers want to give their license to host to people that they can trust, who are going to make them the money for their software. So there's lots of economic incentives to ensure that there's no bad actors.
Yes. So I'm always like, as I think as developer and technologists, we always want to try to find this closed loop, fully perfect solution. But as soon as you hand something off to somebody else, you're introducing gaps there. I mean, they may be small gaps, and we all go out a way to do as much as possible to minimize them. But there's still gaps there, and that's where then the incentivization structure comes in to close them even further, or at least make malicious actors hold them responsible for their actions.
Yeah, it seems like Fluence has the perfect mix of, in this case, you can't fix it. Economic and money incentives can't.
That's where we drive into.
All right, well, it looks like we've answered every question in the chat, and we're just about out of time. So thank you so much for your time today. It was a pleasure being able to speak with you.
Hey, thanks for having me, everybody. Thanks for listening. If you have any questions, please reach out either through Lincoln or anybody else, or directly through us. And looking forward to seeing some really cool projects, hopefully.